Okay, let's start. Let me start for this one. Okay, and today we will talk about from 5G to 6G, the different applications, and also we concentrate on the resource allocation part, which is our group. And we try to link this channel on the left with a Nash on the right, so that to see how could we do the resource allocation. And here first we have the outline. We have 5G to 6G, and 5G is a triangle. So basically, they have, as I mentioned before, they have the eMBB for this immense data communication, especially at the edge. They have MMTC basically for the massive connection to this Internet of Things. They have ultra low latency URLC, ultra reliable and low latency, basically for vehicular network or Internet of 4.0. But 5G, probably only this eMBB implemented. The other two is not quite implemented. So they push into the 6G. So 6G, they have this hexagon. So beyond this 3G triangle, they add this integrated sensing and communication, AI, and ubiquitous connectivity, which is basically your this Starlink, okay, and we show you several prototypes, and also after that we talk about the resource allocation in wireless network, and finally we have conclusion. And this is a 2G, 1G, 2G, 3G, 4G. So basically, for 1G, you have this analog kind of phone. And in this Wall Street, if you have this big first generation phone, you are very rich. Because as I mentioned, the first generation, this cell phone in whole Manhattan area, they can support 7 people. Okay, so basically that means you are very rich. And after that, they have 2G, basically TDMA system, the Nokia phone and so on. They have 3G, CDMA phone, and 4G to 6G, they all use OFDMA. We mentioned this CDMA and OFDMA in the previous classes. And again, this 5G, we have eMBB and this capacity enhancement, MMTC, massive connectivity for Internet of Things, and URLC for this self-driving and Industry 4.0. And the major kind of technique for 5G is massive MIMO or millimeter wave. And so it can provide this data rate. But typically, the odd number of G is not quite successful. 1G, 3G, 5G is not quite successful. And 1G because they can support very few rich people. And 3G, because the pattern of CDMA. And 5G is because of millimeter wave. Millimeter wave, even though they can put a lot of antenna in a small area, because the wavelength is small, but because the propagation nature of the millimeter wave is line of sight. So in other words, indoor is no problem. I can see the access point. For outdoor, how often you see the base station, right? If you don't see the base station, you don't have a line of sight, then you have to use a lower frequency. Then basically it's the same as 4G. So that's reason 5G are kind of a business disaster. And anyway, let's talk about the massive MIMO and the millimeter wave. And here's a demo that we have for this. Let's show.
Ultramassive MIMO is expected to be a key enabler in 6G networks for accommodating diverse user demands. However, traditional MIMO technologies such as phased array rely on high power consuming and highly cost components, which makes it difficult to scale from MIMO to ultramassive MIMO in practice. Against this background, we have developed the reconfigurable holographic surface for the implementation of ultramassive MIMO. Specifically, RHS's densely packed sub-wavelength metamaterial elements into a compact space, holding significant potential to serve as a highly integrated, low-cost, ultra-thin, large-scale, energy-efficient transceiver solution for future 6G communications. We implement a prototype of RHS operating at 26.2 GHz. The RHS consists of a two-dimensional array of 384 electrically controllable RHS elements. The reference wave generated from each feed propagates to each RHS element and radiates energy to free space. A C-ilk resonator loaded with pin diodes of an RHS element can control the radiation amplitude of the reference wave. When both pin diodes are off, the radiated power is large, but when they are on, it is small. The states of the pin diodes can be controlled based on the control circuit with the power consumption of only 2 watts. To verify the effectiveness of the proposed holographic beamforming scheme, we evaluate the beam pattern of the implemented RHS. The RHS can achieve the scanning angles from -60 degrees to +60 degrees horizontally. Based on the prototype of the RHS, we develop an RHS-aided downlink communication platform, which are composed of the implemented RHS, user equipments, UE, and a host computer. The RHS consists of multiple subarrays, which is used to transmit signals. The UEs serve as the mobile terminals to receive signals generated from the RHS. The developed RHS-aided communication platform is able to support 2 test cases of multi-user transmission and single-user beam tracking. In the test case of multi-user transmission, we transmit dual-stream signals using 64 QAM modulator. The EVM performance of the 64 QAM signal is 6.93% within 8%. In addition, the achievable rate of the dual-stream transmission in the RHS-aided communication platform can reach 2.1 gigabits per second per user. In the test case of single-user beam tracking, we verify that the RHS-aided platform can provide high-level signal quality for high-mobility scenarios. Specifically, we perform beam training at each position, i.e., the codebook is traversed to select the code word with the highest reference signal received power for communication. It can be observed that the data rate is stable at around 2.2 gigabits per second. Leveraging rapidly programmable metamaterials, our prototype achieves beam switching within 3 microseconds. In conclusion, this demo is the world's first prototype demonstration of RHS-enabled multi-user communication systems, which has been integrated with CICT Mobile 5G AAAU communication platform for multi-stream transmission. This marks a significant step towards a new paradigm in lightweight, energy-efficient ultramassive MIMO technology. Furthermore, RHSs can be extended to support satellite communications, vehicular communications, holographic ISAC, and other applications.
Okay, this demo won the Best Demo Award in IEEE ICCC, okay, last year.
Ultramassive MIMO.
Okay, and then we come to 6G, and for 6G, okay, let me go back. You have this additional kind of integrated sensing communication, AI, and non-terrestrial network. Okay, and then for 6G, there are many different applications. For example, for VR for education, metaverse, and AR for this surgery, automatic manufacturing. Nowadays, okay, in Shenzhen or this Shanghai, they have the factory. Inside the factory, there's no light. No light, okay, basically, okay, no people work there. Everything robot, and also the location and the communication all through the 5G, 6G sensors. So basically, significantly lower the cost. And the house monitoring and smart home and autonomous driving, yeah. And now, okay, when you go to California, if you in several cities, after you drive to the school, you can ask your this Tesla to go out as a Uber and to earn the money for you. Okay, so things change a lot. Okay, anyway, and the first new things about 6G is integrated sensing and communication. In ESAC, the waveform communicate with the destination. But on the other hand, because the broadcast nature, it also to bounce the target, and the target will send back the information. So in this case, we can do the sensing and the communication together. And obviously, autonomous vehicle is one good application for that. And compared with Tesla, this Waymo is equipped with every sensor, right? You can see the Waymo in Houston with all these sensors around. And then you can have this XR. So for the this Meta is a little bit always too ahead of the marketing. Okay, the eyeglasses is good. Okay, for the smart cars, good, but it's a little bit too early. But anyway, with this AR, augmented reality, all these things will be very important in the future. When you wear glasses, you can go to certain places, you see this building, they can tell you the history, or you go to a conference, you look at the college, your Google Scholar pop up. I'm just joking. And then, okay, for this AR, you need to the location of your head, because for your head position, yeah, it's easy to get from the eye, from the glass. But where you located, XYZ, okay, they need integrated sensing and communication. And for security and surveillance, as I mentioned, my PhD advisor have a company so that okay they can monitor this one, monitor this kind of security and surveillance by Wi-Fi, and also can help for the health. When you sleep, what is your breathing pattern? Yeah, and so on. And for Industry 4.0, and I mentioned, okay, nowadays, if you go to some kind of a very top manufacturer, there's no light inside. So before they deploy this kind of factory, advanced factory, all these 6G, 5G kind of infrastructure have to be there. Yeah, without that one, okay, this 4.0 is yeah, it will be not there. And for space communication, okay, this is my PhD student. Yeah, okay, and he will go to Mars. Okay. Anyway, so here we have this integrated sensing and communication.
Integrated sensing and communication ISAC is a groundbreaking technology that merges sensing functions like tracking, activity recognition, and medical imaging with communication services such as email, texting, and video transfer into an integrated framework. Looking ahead, ISAC plays a crucial role in 6G networks by improving efficiency and reducing latency. Aligned with IMT 2030 and 6G, ISAC drives next-generation mobile technologies. A key aspect of ISAC is transitioning from traditional radar communication coexistence system to dual-function radar communication system, which enables cooperation instead of resource competition. Moreover, ISAC allows for flexible optimization between radar and communication functions by joint waveform designs, where the waveform like orthogonal frequency divides and multiplexing OFDM and orthogonal time-space frequency TFS are used for detection and information. In this demonstration, we showcase the practical implementation of a multi-waveform ISAC system, which integrates radar sensing and communication seamlessly. This setup allows for real-time object tracking and data transmission over shared wireless resources. The monostatic radar platform includes a USRP for signal transmission and reception, an up-down converter to shift signals between baseband and high frequencies, and beamformer transceivers to improve detection accuracy by directing radar beams towards specific targets. The communication receiver includes a USRP to capture transmitted signals for processing, an up-down converter to manage frequency shifting for efficient transmission and reception, and a horn antenna to enhance signal reception and transmission.
This demonstration features an ISAC transmitter and receiver that transmit data packets containing a preamble, start interval, and pilot bits. At the receiver, we evaluate both the user's position tracking and the communication throughput. The SAC-AUX waveform, recognized for its robustness in dynamic environments, is utilized to facilitate simultaneous sensing and communication. The experimental setup is depicted in the top section. In the bottom section, the receiver's tracking of the user's movement is visualized on the left, while the communication throughput performance is shown on the right.
We then compare the performance of the ISAC model with OFDM and multi-carrier TFS to highlight the advantages of each waveform. Here we compare OFDM, MCO-TFS, and ZACO-TFS waveforms in terms of spectral efficiency, mobility support, multipath handling, complexity, standardization, and application scenarios, highlighting the trade-offs and suitability for different communication environments. In conclusion, the ISAC-TFS system successfully demonstrated its ability to seamlessly support simultaneous object tracking and communication. By leveraging the ZACO-TFS waveform, the
The system maintained high accuracy even with user movement. ISAC TFS systems paved the way for research in adaptive waveforms like orthogonal delayed Doppler multiplexing or DDM and resource management strategies. These advances are crucial for applications in autonomous vehicles, healthcare, and smarter cities.
Okay.
Integrated.
And then the next one is about AI. And so basically, especially the general AI. And recently, the Gemini 3, okay, I think this programmer's nightmare, right? Okay, basically for programmer is the end of the game. And also this Grok 5 and this ChatGPT 5.1. And recently on my kind of social media, I see a lot of friends try to have a certain give a prompt, and then all these kind of cartoon or this video, okay, they generate all these things. And so basically, okay, a lot of people will lose a job. Okay. Anyway, so this is I mean, AI example. But on the other hand, okay, we found that, okay, I asked some of my academic sister, her daughter studied some internal kind of design. I think, okay, this is easily replaced by general AI, right? And she mentioned that, okay, yes, okay, but the customer have no idea on what he need. So the role for the internal design is that to understand the customer needs from the person point of view, and then use the general AI to generate hundreds of different kind of cases. And among these cases, okay, by understanding the customer need, select the one that fits the customer most. So in other words, okay, the general AI will replace a lot of jobs, but on the other hand, will create more jobs. So how can you kind of, how can you adapt so that, okay, you can take that advantage, you can become the first people to eat the crab, okay? Anyway, so in here we try to talk about this, semantic communication as one of AI, and currently we are talking about everything about bit modulation. This is a traditional kind of Shannon based, and the level B is this kind of semantic exchange. Basically, tell you the concept, and then this kind of the effect of the third level C, the effect of semantic information exchange. So basically, okay, the key idea is that on the level A, on the right-hand side, is basically transmission bit. But instead of transmitting the information, is in the level B, if the transmitter and the receiver have a common knowledge base. And in this case, okay, you don't need to transmit all the information. And then you only need to transmit a very few things so that the receiver will understand. And for example, okay, when you first get married, okay, that is level one, symbol layer communication. You talk a lot, blah, 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 talk a lot. Everybody try to, this is kind of Shannon based. But after 20 years of marriage, yeah, my wife don't talk with me, but only have an eye. Look at me, I fully understand what's meaning. So because on the transmitter side and receiver side, we have a common knowledge base. So in this case, we can significantly reduce this kind of communication. Okay, this is a kind of a semantic communication. Okay, and here we have another demo in this Glocom.
We aim to deliver immersive experiences, massive connectivity, low latency, ubiquitous coverage, high-driven communication, and integrated sensing. Traditional communication systems often face inefficiency and data loss, which hinder performance. In contrast, semantic communication could overcome these challenges, ensuring more efficient 6G. Did semantic communication follow Shannon-Hartley theorem? Yes. Semantic communication maximizes the transfer of meaningful information under fixed bandwidth and channel conditions, improving inference accuracy and transfer reliability while aligning with the Shannon-Hartley theorem. What about current AI algorithms like generative AI? Do they fit well into this? Most AI algorithms, including generative AI, overlook channel errors in their encoders and decoders, limiting real-world performance. Semantic communication can address these issues, enhancing their effectiveness. Additionally, generative AI can enhance semantic communication through keyword extraction, background knowledge provisioning, and content reconstruction. First, we propose a semantic communication framework for video conferencing with generative AI. Diagram of our system. The first frame of a reported talking head video serves as a shared reference, while the transmitter sends predicted frame semantics for the receiver to generate the video. This is the hardware architecture and key parameters of our video transmission system, with data sent and received via USRP and real-time results shown on screen. This showcases semantic coding performance under occlusion, where video transmission remains unaffected, maintaining high quality and low latency. This demonstrates H.265 performance at the same bandwidth. Packet loss disrupts video transmission. Posing the limitations of symbol-based systems, the semantic communication overcomes.
So this is basically, as I mentioned, for Starlink, okay, for uplink, you can only have 5 to 6K because the transmission power and the distance 550 kilometers above. So in this way, there's no way you can transmit a video, FaceTime like the traditional way. So in this case, what you can do the semantic transmission. On the receiver, they may have some kind of your photo as a file. And then when I transmit, instead of transmitting this kind of video, I send, okay, this guy is rotating side for how many degrees? This is a very small information, right? In the receiver, they use the AIGC to generate this one. So by doing this one, they can use a very narrow, 5 to 6K kind of data so that you can still have the FaceTime, right?
Next, we propose a semantic communication framework for underwater image transmission, which uses large language models to compress and prioritize semantic information from underwater scenarios and reconstruct the images by diffusion models on the surface. In detail, the semantic encoder identifies key regions and compresses images by large language models, while the semantic decoder applies control net guided by both keys and global vision to reconstruct the image. Here's the example. What is the status of the diver? The diver appears to be actively swimming underwater, equipped with full scuba diving gear. There is no abnormal situation. What's around the diver? The diver is in a murky area with bare branches on the seabird and disturbed sediment. Here's another.
Okay, and let me go to here again. Yeah, so the key idea here is that, okay, in the receiver, there's a large language model to hallucination, bullshitting. So basically, it's say whatever thing. The purpose for transmission is not for the source. It's not only for the source information, but try to send some information to prevent the receiver's large language model or diffusion model from hallucination. So my purpose is the receiver, you can say something about this diver or something like that, whatever, but I need to give you some description such as you generate something which is not outlandish. It still makes sense. You understand my point, right? So in this case of the communication, it's beyond the bit. It's prevent the receiver's AI from hallucination. So this is different. And then the third one.
Relay channel. The robot shares its view, and we sync data between Earth and Moon. After sending a command, Earth predicts the updated view. Turn right if the view matches. The robot sends a small acknowledgement. For moving forward, changes occur. The robot compresses the difference and sends it. Updates its prediction with the received data. In summary, semantic communication for video conferencing saves 67% bandwidth compared to H.265. Future work will explore low bitrate satellite communication for image and video transmission in remote areas for disaster monitoring. Semantic communication for underwater image transmission reduces data size to 0.8% while maintaining high quality. Future work will focus on exploring additional applications in marine biology research and environmental monitoring. Semantic communication for lunar robot control saves bandwidth, enabling efficient command response prediction. Future work will explore predictive algorithms to anticipate lunar operations, reducing the need for real-time command synchronization.
And the third for the space, the moon is 2 seconds. So Mars is a few minutes. So basically, okay, when it communicate with me, it's something happens before, right? 2 seconds or a few minutes before. So in locally, I don't know the real time what happened there. In locally, I have to use the AI to predict what is the current there. And then I send the information to have the instruction. So in this case, okay, this is on the Earth side. I need to kind of a large language model to imagine what happens there, I mean, a few seconds ago, okay, real time, okay. So basically, this is a kind of semantic communication. Okay, and the last one is about this ubiquitous connectivity. Both is called area access network. It can combine with this satellite, high altitude platform and UAV and ground and even marine together. So typically for UAV, okay, you can have a lower height, minutes to hours, small changes. Coverage is small but dynamic. And recently, okay, you're seeing this Ukraine-Russia war. You see a lot of UAV. It's very important for this military one. But back in Shenzhen, okay, they have this low economy kind of low altitude economy. So basically, okay, when you have a the UAV will deliver the food to you at your backyard. Okay, so all this instead of this Amazon people just drop in front of you, this UAV will come. So that can happen in Shenzhen, but not in Texas. In Texas, if some UAV fly on my backyard, I have a shotgun. And then thanks, Scott. Okay, and I'm just joking. And for the hub, okay, high altitude platform, okay. So basically, fly above this weather and then stay there for months. So what is the advantage? For example, we used to work for a kind of a company, and during this kind of, for example, this Amazon Prime Day, and they use they need a lot of machine learning, try to calculate, try to predict that, okay, what you want to buy. Okay, in this, for example, you buy something, they give you a lot of suggestions, right? Those are all by the machine learning. Okay, so in this case, this hub will take a lot of kind of GPU on top of the city to the edge computing to support all the metropolitan area. For example, so Houston, we have a hub on the top, so every base station have the power for the edge computing, right? And then they can predict what you want to buy. And the next year we have World Cup. And then everybody want to see the World Cup, and then they will bring a lot of cash on the top, so that okay, they can send to everybody about this video clip, right? So all these things, so this is a hub, and for this also okay, we have a demo with Saudi Arab. For Saudi Arab, okay, what's the problem? The problem is that okay, most of the infrastructure is along the coast. In the middle, they're all desert, but those deserts have a lot of kind of people on the camel. Okay, they go around, and in this case, they still need some kind of connection. So, but building a base station there will be very expensive, and also serve nobody all the power. So what they do is that they bring 20 hub on top of it, and then they cover all the desert area. So those people in the camel, they can look up to the hub and then still can communicate. Okay, and finally, there's a satellite and the Starlink. You can see all this kind of news. Okay, this is a demo that we did this year.
A space-air-ground integrated network for enhanced communication, computation, catching, and control in 6G. Wireless coverage is a key issue in 6G ubiquitous communication to support scenarios such as aviation surveillance, low-altitude economy, and Industry 4.0. However, there are some urgent issues in wireless coverage to realize 6G ubiquitous communication, including no coverage in specific areas due to coverage differentiation caused by the law, lack of coverage in low-altitude areas due to coverage void caused by the dynamic UAV, and weak coverage in dense areas due to mismatch between the user needs and service capabilities provided, which is shown in the last picture of Milan's cell phone call map. To address the above issues, the integration of communication, computation, catching, and control is designed to enable seamless connectivity, efficient data processing, optimized content delivery, and intelligent decision-making for next-generation services, which can integrate ad hoc network module, flight control module, backhaul module, core network, backhaul equipment, and satellite module on air flight access point platforms. In test case 1, we have performed multiple practical trial application tests for the prototype system of the space-air-ground integrated networks.
Our results demonstrate that, given an reference signal receiving power threshold of -100 dBm, our prototype system is capable of realizing the coverage area of more than 100 square kilometers, where the reference signal receiving power of the ground user exceeds the threshold. In test case 2, due to the dynamic nature of UAV users and satellite networks, satellite links are frequently switched, which can cause performance loss. In this regard, we design a reconfigurable link allocation method. The results show that under our proposed method, users and satellites are able to preserve the connection while resource efficiency is improved by more than 40%. In test case 3, features of
Okay, and for the first two test cases, okay, for the UAV, okay, when bring your kind of food toward you, okay, they fly in there. What's the problem? The problem is that the base station is antenna is looking down because all the customer is on the ground. So when even the UAV fly next to the base station, okay, there's no signal. So in this case, what you can do? And what we do is that, okay, we have a higher hub or higher flying UAV. So those lower UAV will look up to communication and then at the relay back to the ground. So in this case, it can work. And it's also like this Starlink, okay, this SpaceX, they can have this real time kind of showing this big rocket going back. How is possible? Because when it's come back, there's due to this kind of friction with air, there are big plasma below, so that this plasma is a kind of conductor. There's no signal you can come down. So in this case, this is called blackout. So every time, okay, in the traditional way, okay, when this spaceship come back to the Earth, you lose the communication for 2 to 3 minutes due to this plasma. But why? How come the Elon Musk can show the real time? Because they have Starlink. Inside, they cannot communicate down. They can communicate up to the satellite, and the satellite relay back. So by using a similar idea, okay, we overcome the problem of the UAV cannot talk to the base station. Okay, and the next one is this
HAPS mobile communication
in Japan.
systems include ultra-wide coverage area, disaster prevention, and three-dimensional space area. We simulate the multiple HAPS over Tokyo areas for collected heterogeneous user equipment distribution. We collect user equipment distribution over Tokyo on January the 1st, 2021. By employing 3 HAPS, we compare omnidirectional antenna case, beamforming with 2D information case, and beamforming with 3D information case. We can see that more information, the beamforming can serve the UEs more efficient. In test case 4, building space digital twins is hindered by high latency, limited bandwidth, and unreliable networks. As lunar missions grow, a new system is needed to manage cislunar networks. This work proposes a DT-based scheduler using network state and mission priorities, integrating age of synchronization and time-triggered Ethernet for optimized data transmission. To build the network's DT, physical layout data is captured in a matrix, enabling extrapolation of future communication paths. Routes from missions to Earth are then constructed and allocated based on priorities and capacities. This routing information is shared with all missions to determine their capability. This demo is already partially deployed in the commercial networks of China Mobile, providing coverage assurance for emergency incidents. It designs an integrated 4C module that sets a new benchmark for the integration of multi-dimensional networks in the evolution towards 6G. Furthermore, there are various applicable areas, such as aviation surveillance, emergency rescue, and low-altitude economy.
Okay, I think for the last example, okay, this is my astronaut student. When you go to the Mars, okay, you need some kind of relay in the middle, because sometime, okay, all this go back to the Mars, moon, okay, go to the moon, okay. If your spaceship is behind the moon, okay, how could you send the information? Moreover, sometimes, okay, the Earth's direction is on the back, they have sun. That I mean, the science behind the Earth, all this radiation, okay, when you go to that direction, okay, all the noise is there. So you have to find a big route, right route to send the signal back. So what he's doing is in that part, okay? Okay, and so we already talked about this 5G to 6G, and now let's try to talk about our research area. We are working on the resource allocation and environment network. This is my label. Okay, and then okay, among the resource allocation, instead of doing the centralized control, we do the game theory. So we have two game theory book, and finally we have conclusion. And in the second part of the class, okay, I will try to talk about the game theory. It will be a fun part. Okay, how to play the game in the wireless network. So for the resource allocation, typically you want to have a certain objective by changing some parameters. For example, the transmission power for the different people. Yeah, if I speak aloud, very loud, it will be interference to you, and vice versa, right? And you can also change this modulation, which channel you have. I mean, channel coding, all these X1, X2N, this is a parameter you can change. And under some constraint, you have an equality constraint and inequality constraint. So in this case, it's a constraint optimization problem. And also due to the binary nature, so such kind of problem is typically kind of a mixed integral programming problem. So you have continuous and you have integral part. In this case, it's non-NP hard, non-polynomial hard. So in other words, for small area network, it's fun. But for the large network, you have hundreds of users, the complexity is uncontrollable because the complexity exponentially go up. So in this case, this motivates us to have this distributed control. So for this centralized control, the pro is many available solution can achieve better results because the centralized control can handle more challenging problem and fit current cell phone network. When it comes to 1G, 5G, 1G to 5G, the system become more and more concentrated until 6G. Because 6G, you have a Starlink, you have this kind of terrestrial T-Mobile. Nobody can control each other. And in this case, you need a distributed optimization. So, but the con for this centralized control, a lot of signaling, right? So basically, okay, in order to do a centralized control, I have to monitor everybody all the time. That is, I mean, not working. And the delay can be high, poor scalability because only small network, large network, NP hard problem. The complexity is too high. Security and privacy issue, I have to. The base station is a dictator, it's a kind of slavery, okay? So basically gather all your information and control all your phones control information. And poor heterogeneous network, poor for heterogeneous network. So in this case, we try to have this distributed solution. So in other words, user one only control is a control variable x1 to optimize itself by considering the user two as a opponent, and vice versa about user two. If you previously one, okay, this control both x1 and x2 centralized control. Now, okay, user one control its own, user two control its own. And in this case, we will have a kind of a game between that. The most important game is called Prison Dilemma. So basically, okay, we have Henry and Dave, both got caught by the police. And if they both play cool, okay, they don't kind of blame each other. And the police, the FBI can only sentence them for the tax evasion, right? Like Al Capone, okay. So they go to jail for 2 years. And if kind of, Henry blamed the Dave, well, the Dave still play cool. Then in this case, okay, Henry have this kind of victim kind of, not victim, this, how to call it? If you say some truths about to the FBI have some protection for you, right? So I don't know how to call it, okay. But anyway, this Henry goes to jail for 1 year, the other, Dave go to 5 years, and vice versa. And if Dave blame Henry play cool, and then okay, this Henry go to jail for 5 years. But if both blame to each other, the police know everything, right? So both go to this kind of jail for 3 years. So in this case, you can see that okay, even with a centralized control, you have a better solution 2 years. But because everybody is greedy, everybody want to have 1 year. And then in this case, everybody blame with each other, police know everything, both go to jail for 3 years. So this is called price of anarchy. Yeah, because everybody greedy, and the overall system performance will be worse compared with the centralized solution. So what is the Nash equilibrium? The Nash equilibrium means, okay, if the other is not moving, you are moving, you will get lost. So look at this case, okay, both blame to each other. If one of them change from the blaming to playing cool, keep silence, then okay, they will have the prison from 3 years to 5 years, 3 years to 5 years, will benefit the other. Then why should I do it, right? Why should I do it? So this 3 year and 3 year, even though compared with this solution is have a worse solution, but that is a stable, it's a Nash equilibrium. So what is Nash equilibrium? You can see about the boxing, and finally two people hack together. That is Nash equilibrium, because only the ref can keep them away. If you want to push away, the other hand is right on your face, right? So in this case, that even though it's not good performance, but that is Nash equilibrium. So this is a Nash equilibrium. And the price of anarchy is that, okay, well, the distribution solution is good, but unfortunately, okay, the performance will compare with centralized solution, it will be poor. So how could we close the gap between the centralized solution and the distributed solution is basically our research area, okay. And so for the game theory, we have a non-cooperative game. And for example, for the sport, we have a zero-sum game and boxing that I give you the example of equilibrium. And for the repeated game, if the game played multiple times, then okay, it can have some better performance. Why? Because in 2005, in the Nobel Prize, is from a professor from the University of Maryland where I graduated. At that time, I was there. And his research is called try to analyze the Soviet Union and United States kind of behavior during the Cold War. It's called MAD, Mutual Assurance Destruction. Why? Because the game is in the Cold War, the game is played multiple times. If you attacked me with nuclear attack first, your short-term gain will be wiped out by the future retaliation. Yeah, and in this case, okay, if you are rational, you will not get this short-term gain, right? So in other words, okay, for the collaboration, I tell to my student, okay, our collaboration is a lifetime, okay. So basically, okay, I will benefit you, you will benefit me, okay. So basically, this is kind of in the future, okay, we can benefit to each other. So by a certain, but this is by a certain threat of the punishment. Okay, so this is a kind of a repeated game. Why it can close the gap of a price of anarchy? Because if you betray me now, I mean, I will take T for time in the future. So you'd better behave. So this is the basic key idea for the repeated game. And then they also have the evolutional game for the nature, how to evolutional, how this kind of animal can be behaving this way to fit this situation. And this is a repeated game, evolutional game. And also a part of the type of repeated game. And you have a Bayesian game. So the Bayesian game basically means that, okay, at the beginning of playing, I have no idea about what you do. But now, okay, just now, okay, my student visited my office, even by hearing the knock, he knocked the door, I can predict what he wants to say. Yeah, the different way of knocking the door, I understand. Okay, so this is called Bayesian rule. So by interaction more, okay, I know the other's behavior, and vice versa. The other also know my behavior. So in this case, okay, we know each other, and then yeah, as if okay, when we do the action, I will not only consider my own benefit, like the Nash equilibrium, but also consider the other, because I already have the belief about the other. So when we do something, I provide some solution that both of us agree, right? So basically, okay, we put something on the table. I understand your need, you understand my need. So I put there, this is the mutual information, and we immediately agree. So this is basically Bayesian. I know by interaction, I know what you need. And then in this case, I have some kind of offer that you cannot deny. Okay, so this is the basic Bayesian rule. And the bounded rationality. So basically, okay, this is Nobel Prize for 2002, and it's called prospect theory. So or suffer about this gain and loss is different. Okay, if you have a, for example, if you have a higher probability, give you an example, okay. You have a 1% to earn $1 million, and you have a 100% to get $5,000. Which one you get? Yeah, most people select that $5,000, right? But you calculate the probability. Isn't it the first offer first offer is a better has a better utility, right? So human have this kind of different reaction, and then this is for the marketing. Marketing and this human kind of thing, and you can utilize this one to do a lot of advantage. Okay. And this auction theory. Auction theory win the Nobel Prize 1996, and it's too complicated. But I found this video. Sorry, the title. Okay. Anyway, so and let's quickly go through some of the most representative game and also very interesting one. And there are many different types of the game which is in your book, but here I just show you some example. For the first about the non-cooperative game. The non-cooperative game, we have a finite set of user n and set of available strategy. For example, what is the power, what is the kind of channel, what is the modulation that I have, and I have utility function. Utility function based on the function that based on this kind of action and the other action. This x minus 1 is the other action because my transmission power is the interference to the other. So my utility function is not only depending on my action, but also the other, right? So while in the final exam, I have this ranking for the first, second, and third one, for the homework, midterm, and final. That's because I'm trying to introduce a game among yourself. So your score is not depending on your performance, but also depending on the other. So by doing this one, okay, I'm not your only enemy, okay? Anyway, so this is a game theory, okay? And then they have the complete information and incomplete information. For chess, it's a complete information, okay? Because everything is on the table. And some between the company, between the country, they have a secret, things. This is incomplete information, okay? And this is a Nash equilibrium. And then we also have a concept called Pareto optimal. So the so-called Pareto optimal is that, okay, for the Nash equilibrium is poor, but we want to improve it to a certain point that, okay, if I want to improve my performance, I have to hurt somebody else. So this is called Pareto optimal. And among these Pareto optimal point, which one is more fair, social fair? And we want to control our game to the point that, okay, and to the point that, okay, that is the boundary of the best thing we can do. But when we divide, okay, we divide according to certain fairness kind of criteria. I tell my PhD advisor, for example, when we try to set up company, you put a kind of $1 million there. I put a kind of $1,000 there. After that, we got the gain about the $1,001, and how much you get, how much I get. Yeah, depending on how much you invest, if you get $1,000, I got $1, right? So this is kind of fairness. Okay, and so this is a kind of called Pareto optimal. This is the Nash equilibrium. Nash equilibrium, you see that from the Nash equilibrium, both can improve. And in this case, okay, the Nash equilibrium is not kind of Pareto optimal. But from the Pareto optimal, if I change to the other, somebody must hurt. And in this case, okay, is a Pareto optimal. Okay. And then for the spectrum sensing, okay, okay, we want to see that, okay, the sensing part on the X and the rate, integrate sensing and communication. For the communication is a Y and the sensing is a X. And these two are conflict kind of performance. And we want to try to see this Pareto optimal and maximize this Pareto optimal. such that within the same performance, sensing performance, we want to maximize the overall rate, and within the overall rate, we want to, with the same overall rate, we want to optimize the performance, sensing performance. So this is nice equilibrium. And the second game is a cooperative game. This is my career word, okay? So basically, okay, we have a coalition and a number of user A, and we have a coalition. And so basically, the value of the coalition is VS, and VN is a grand coalition that will include everybody. And after we form a coalition VS, we try to divide the coalition, the value of VS into the payoff, X1, X1, X2. And in this case, okay, we have this kind of division. So basically, okay, this look like if I, that during the history, okay, that this British, okay, have the coalition with France, and next with against France, and something like that. Why they do that one? Because they form the coalition so that, okay, they have mutual benefit, and after that, they divide. So this is basically concept for the coalition. And the very simple example is this kind of a presidential election. And for example, totally we have a n population of n. If you're kind of the size of your coalition is greater, either Democratic or Republic is greater than half. Okay, suppose we are in Europe, not here. Okay, and and then you win the coalition. And after win the coalition, how could you divide the pie among your people, right? So this is basically, okay, very simple coalition, okay. And there are different types. They have the grand coalition. So basically, in a big company, we have grand coalition. We don't want the people to leave. And how could I give the incentive? For example, this open Meta have how much money to buy the OpenAI people, right? And then you have to make sure that, okay, you give enough incentive for those people so that they will not jump to the other company, right? So this is kind of first thing. And the second thing is that, okay, for this coalition formation game, suppose I have a kind of project. This method we don't have project, okay? Suppose we have the project, and suppose the project is in group, but for in group, and then the first thing you want to see, okay, which people I want to work with, right? I don't want some kind of free rider and something like that. So in this case, you guys will automatically form a group so that you guys have a mutual benefit, because anybody have a free rider, you just kick him out, right? So in this case, and the third type is a grand coalition graph game. So inside this coalition, you have structure. Who is the CEO, who is the CTO, or something like that. Inside, you have a certain structure. And then we have this for the second game, coalition formation game. You have this very simple solution called merge and split rule. So in the game society, they call it the marriage and divorce game, but not politically correct. So we change to the merge and split. So suppose in the group, okay, for the project group, if you find somebody that join, they can bring the mutual benefit for everybody. You just include it. It's a merge. If you suddenly found this guy is useless, you just kick it out, right? This is called split. So this is very dynamic. Okay, very quick. It can converge to the optimal coalition formation, and so that the people work with each other, right? So this is kind of coalition formation game. And for academic collaboration, so when I work for the other, and I try to, for example, when I first came here, I only have game theory. My PhD dissertation is about game theory, and I work with Rice University for this big data optimization. And then, okay, we work together. Everybody have something on the table. It's a mutual benefit so that we can form the coalition, right? I need to bring something for the other, right? The other have benefit, then I can work with the other. And after that, okay, every time I have a coalition, I get a new card because my student will study some new things. And then I got a new card. Now I have two cards. And then I try to talk with the other people. I started new things, and more, I have more and more cards in my hand, so I can play with multiple people. So this is how I grow my kind of research. And also, okay, somebody works with you for a long time, and probably it's saturated, both know each other well. So in this case, okay, it's better to let the people to work with the other. So let's have a divorce. Okay, sometimes the marriage is easy. You go to Las Vegas, 1 hour, you get married. But when you come divorce, okay, it's a NP hard problem. It's very, very difficult. So basically, okay, in academic, okay, try to, I mean, at least, okay, when you have cooperation, long-term cooperation is okay, but when the people separate, you think it's a good sign because he or she may study some new things. Maybe after 5 years, when he come back, when or he or she come back, you study some new things from what his or her experience during the life, during those experience. So anyway, this is a merge and split in academic. And the next thing is the matching game. The traditional matching for the resources and for the user is an n to the power 3 complexity. It's a very difficult. And then we want to have suboptimal solution, basically means matching game. So the basic one is there are many different games, and here we have stable marriage. Suppose we have an agent of man, agent of woman. So we have an agent of service, agent of user. We try to match together. And we have the preference list, okay? And so what is our preference list? I mean, Taylor Swift and Lady Gaga, whatever, this is your preference list, okay? And for men and women, they all have the preference list. And after that, we have the blocking pair. So what is the blocking pair? A married man love a married woman, and this married woman always also love this married man. So what is the solution? Both couples divorce, and this married man marry that married woman. So this is a system, means system unstable. We want to have an allocation that we don't have the blocking pair, so that the system is stable, right? This is look like British royal family. I'm just joking, okay? And, and then we want to find a solution that is a stable matching, that the system is stable, even though it's not global optimal, but because everybody want to have a top of their preference list, so it must be kind of near optimal. Then moreover, okay, Gale sharply have this kind of a solution, and then it have a complexity of O(n) instead of O(n) to the power 3. So because of this, Sharpley won the Nobel Prize in 2012. So let's have an example. And we have a size of man and size of woman, and both have the preference list. Adam like this guitar better than Heike, better than Irina, better than Frank. Begin to date guitar. And Bob like Irina, and Cars also like guitar. And Gita think Cars is tall, handsome, and rich. So damn is Adam. And Adam have to find the second preference list. And David also try to PK with Bob for Irina. And Bob becomes a spare tire. And then Bob becomes to date the second on the preference list friend. And very quick, yeah, it got convert. How quick it is? For my new PhD student, 1 semester they convert. I cannot believe it. At the beginning of the semester, they look like this. And at the end of the semester, it's changed. Anyway, so this is a quick. And for reviewer assignment, when you submit a paper, and what is the paper assigned to the reviewer, they have the matching. And you know that it's always the third reviewer to screw you up, and all this cartoon and something. Nowadays, when you submit to the paper, all the paper is reviewed by the matching game. Okay, so they find some related. Anyway, enjoy. Okay. And for Toyota, we work with the Toyota for this task and for this edge computing for the federal learning. And then we try to have this different goal for this. Anyway, so finally, the contract theory. And now finally, okay, the contract theory. So for contract theory, okay, they won the Nobel Prize 2014 about the asymmetric information. So asymmetric information. So what is the asymmetric information? And they have 2 types. One is before the contract, which is called adversary selection. Let's say, okay, my PhD student. So basically, okay, if I ask my student for interview, what do you want to do? I want to become a researcher. I want to publish. You want to graduate, okay? But you know that I want the publication so that I can report to my funding agents, but I don't know your plan. So basically, okay, the real plan is to find an internship And the secret plan is try to become a baker, rock star, writer, and so on. So in the case that, okay, they have information asymmetric. So in this case, okay, typically for my student, and for suppose I ask, okay, are you good at programming? Are you good at mathematics? I don't know. I don't know the student. Or the student will always reply, I'm good at both. So because he wants to get the financial aid, right? So this is the information asymmetric. So in this case, I provide the two contracts. One contract is for the theory. You study some deep theory. And after that, I give you the application that's used here. The other is, okay, let's go to the newest application. I have existing solution, and then I apply there. This is for the programming. So you select the choice. But because you know that you are good at mathematics or you're good at programming, you will select the one that fits you most. So in this case, by providing the multiple contract, I overcome this kind of information asymmetric because you are rational. You select the best one for you, and immediately I know what type of person you are, right? So this is the kind of things. And after this contract is called moral hazard. So when my parents think I'm doing, and when my advisor think I'm doing, when I'm actually doing that, I'm in the office. And if I'm travel, my student have party, that's obvious, right? How could I motivate the student to do that? Okay. So the solution is that I try to align the student and my interest together. This is a moral hazard. For example, okay, for the mainland student, okay, they say that 4 years, you have 3 papers published, you graduate. For me, it's that, okay, you have 3 papers submitted, 3 papers submitted. 3 papers submitted, 1 accepted, you graduate. Look the same, all 3. What's the difference? For the first solution, the student will play hard in the first 3 years. In the last year, the student will find an advisor. The advisor will be the slave for the student to work for the last year for the publication of 3 papers so that student can graduate, right? For the second solution, I align my student kind of interest together with publication. And the earlier you finish, the earlier you graduate. Then immediately give you the incentive. You want to go out to catch the last wave of AI, right? And to get a job. Yeah, obviously you have the incentive to work hard. Okay. And another example is that, okay, people say that, okay, this is a threshold. You have to publish above this quality. And then all the students will only publish on this threshold, easy to publish, right? This is a human nature, right? And then how could I change? I say that, okay, in the future, your employee will have no idea about what you published, no idea about what you're doing in PhD, but they will see that where you publish. If you publish in some garbage kind of journal, that means you're not that good. If you publish in a top journal, that means you are the good. So I suggest you to publish in a good place. If it's not go through, let's go to the second tier. But no matter how, let's take this for the top one because it's also benefits to you. So by doing this one, I align my interest with my student interest, right? So in this case, I overcome this kind of moral hazard. So this is a kind of a contract theory. And so basically, my students using this blockchain for this kind of crypto economy. He published he published a kind of book about the crypto economy, and then okay, go to this company before the COVID, right on the time for the stable coin, and his starting salary is 3 times up to me. I'm a chair professor. I look at him, her, okay. I mean, will you have some kind of summer intern for me in the future? So basically, it's right on time for stablecoin. And she's already financial free for this, due to this. Anyway, so this is the case. And this is the crypto economy and the penalty and so on. So I can go quickly go through this one. And this is the book she published. Okay, this Dr. Jing Li. Okay. And finally, then we have the mean field game. So the mean field game is for the classic game, okay. If you, for example, I went to this Atlanta last month, and Atlanta have the world's largest aquarium. Inside they have a big shark, and then have a group of fish. If the shark try to attack the fish, and then you can quantify this one as a dynamic game. but there are hundreds or thousands of fish. So in this case, when you try to formulate, you will formulate very complicated. But this fish will form something like a cloud. It's moving around, right? Moving around. And then in this case, okay, you can quantize all these kind of fish as a field called mean field. And when the shark try to attack this group of fish, and the shark will attack using some algorithm called HAB. And this group of fish will react according to some algorithm called IPK. And then in these two cases, we can have the equilibrium as if there's a kind of a two user, shark and a group of fish. So in this case, you can simplify the dynamic game a lot. Okay, so this is called mean field game. And so mean field game started the Nash equilibrium involving large number of symptotic neglected user. And then in this case, they are indistinguishable, very small. Everybody is rational, and also everybody has a different state in the heterogeneous. And then we can have this by using the mean field game, we change to a standard control problem so that the solution will be simple. So here we do a very nice comparison. Okay, on the left one, this is an optimization problem. You control a variable mu by for objective function. And for game theory, okay, your utility function, the ith utility function, not only depending on your action ui, but also the other mu minus I. So your score not only depending on you, but also your classmates. This is the game theory. And for optimal control, so basically you minimize a kind of function by a dynamic constraint. So the differentiation equal to constraint. For example, for this Starlink, this rocket going up, going down, and differentiation of location over t is a speed. Differential of the speed over this t is acceleration. Acceleration is equal to force, right? So in other words, okay, all this Starlink control is this Starlink SpaceX, this rocket going up and going down, and they all work on this optimal control part. And if you have a two kind of optimal control part, and for example, this is okay. Related to, but that is limited to the linear function. Yeah, there in the Starlink, they have a lot of nonlinear, unpredictable control, weather or something like that. So it will be much more complicated. Okay, and for differential game, basically, okay, it's a kind of with a differential with the ODE, but you have a game part. And for the game part, if you have thousands of users, then how could you do it? So you make this group of fish into the mean field. And in this case, okay, you do the mean field control. It can greatly simplify the solution for this. And here we use the mean field control for this Manhattan. This is a Manhattan bridge. And this is a kind of Manhattan bridge for this edge computing. This is the work by Toyota. And on the left-hand side is a mean field. And all those cars try to have the kind of edge service. We can say that delay requirement can be satisfied by the mean field control. On the right-hand side is by the victim algorithm, the current state of art. We can see that okay, the delay control, because it's too complicated, is not satisfied. So in this case, okay, we can see that okay, the mean field control for edge computing can do a better job. Okay, finally, we have this game with machine learning. So basically, okay, this is a Nash equilibrium, and this is a kind of this is a three Nash equilibrium. And then, okay, so we have a game. This game is called chicken game. What is the chicken game? Two gangsters, fast and furious, try to drive the car against each other. If they play cool, and then nobody kind of turn away, they both dead. Okay, their payoff is very low, very low. But if it's a certain probability, if one of them go away, the other still play cool, then the other look like a chicken, right? Scared. So this is called chicken game. And in the chicken game, you have something that is outside of the convex hull of Nash equilibrium. And in this case, okay, how could you learn through this one to the outside, the convex curve, nice equilibrium, and my student using the machine learning try to learn it out. And then this is this is a correlated equilibrium by this Nobel Prize 2005. And my student work on this one. After that, he work on this JP Morgan. And after a while, okay, Google read this paper and then try to send him an email. And finally, he's now in this Google Gemini group. So I don't know how much money he have earned. Yeah. And anyway, so this is basically, okay, a very kind of example because, you know, they want machine learning is a black box. They want to have some theory to guide for it, right? So here is some kind of theory for this. Okay. And finally, okay, we have some other work with quantum computing. So we have the quantum computing. My third PhD just graduate. Quantum computing is generated for the multiple ring universe. And this is very good for integral programming because for integral programming, if you have n integral programming variable, it's 2 to the power of n complexity. Then, okay, when n become large, there's no way you can use a classical computer to do it, right? So you're using this quantum computing to generate, you only need n bit to generate this 2 to the power of n, this kind of parallel universe. And among this parallel universe, if you have a continuous variable like a power, you can use a GPU. GPU, they have gradient, gradient method, you can easily find it. So you use a GPU for the continuous variable and quantum computing for integral programming. In the middle, you use a Bender decomposition to link them together. So in this case, you can easily kind of link this kind of use both GPU and this quantum computing together for the sophisticated problem. So my third PhD student just graduated for this one. And this one is Amazon Research Lab. We got this marketing. And so basically, okay, they use the eye tracking. So when you look at the phone, try to book something, they can keep track on where you look at it. So by looking, for example, when you do the shopping, and when you do this kind of let's say Christmas, you want to go to some places, you're using Booking.com, and then different people have different way, right? You guys look at like the location, and I look at the price because I'm a family guy, and the ladies probably look at whether or not the picture is nice or not. So by looking at this kind of information, they can customize your kind of interface to fit what you need. So we successfully get this Amazon research funding, which they only fund for internationally for this marketing research. And they asked me why we want to fund me. I say that, okay, when you gaze as an apple, the apple also gaze at you. Okay, this this philosophy. Okay, so basically, okay, and we also have this another this kind of this robot to have wireless charging. So when you go to the Mars, okay, there's no kind of battery. Nobody can change the battery, right? We have this robot to wireless charging for this kind of sensor, so that the sensor network maintain. And after that, my student really work in the NASA. Okay, and the smart grid. Okay. And this is a UAV try to have the environment protection to see where the oil leak, and also we do the carbon neutralization. And but after last presidential election, I changed to biologging. I'm just joking. Anyway, I'm just joking. Anyway, here is the conclusion. We have this resource allocation. In the first part, we talk about what is 5G and 6G, and then okay, after that we talk about the game theory. And which is one type of the distributed resource allocation, which is in our group. And there we also have some other group work. You can go to our lab website. And finally, okay, in our group, we have many great activity. And you see, even during the COVID, yeah, we have this kind of social distance soccer. Okay, so people are keep a distance to each other. And also you see, I'm very nice. Okay, I'm very nice people. This is me. And my student who could not meet the deadline is far away. Okay, I can easily try to enhance my student productivity. And also we have all these kind of different activity and so on. So if you have interest, yeah, we can talk about this I mean, future graduate study, but most likely I only support for PhD student, and also due to the government shutdown, okay, my new funding is not coming. Okay, all this funding is got pending, so currently I don't have extra fund, but I hope that okay everything come to the back to normal. But no matter how, okay, after this class, if you get A, if you need some kind of reference, feel free to ask me for that. Okay, so anyway, I think let me stop. Okay.